Okay, so we're back, and this is the last little part of this lecture, and I just want to give you a quick sort of overview of agent-based modeling. Agent-based modeling is the focus here is not on the kind of temporal processes the same way as they are in discrete event system simulation and system dynamics modeling. Here, really, the focus is on interacting individuals. This is kind of the most microscopic, most sort of low-level simulation type. So you have, in this case, you have agents that are, and those are the sort of entities of the simulation model. They're called agents here. And those agents move around they move around space typically. And so they actually, you typically simulate all of this spatial relationship. So you really do care about how long it takes for an agent to move from one spot to the next. But rather than modeling that as an activity, like how long to get from point A to point B as a random time, you actually just move the agent along at a constant velocity and then keep track of how long it takes until it gets from point A to point B, and other things might get in its way along the way that it's going to have to deal with. And so you're actually really simulating kind of a whole world, like you can see here in this example of these this kind of wolf and sheep predation model here. So you've got, they've got brown land, which is kind of dirt, and then the green one is kind of grass that the sheep can eat. And then you've got these wolves that can eat the sheep, and they're all moving around randomly. So the sheep have to find grass randomly, the grass regrows randomly, the wolves have to find sheep randomly, and you end up getting these dynamics, down here, that are kind of outputs of these models. And you can see they're very jagged. There's not necessarily a lot of pattern, but you can kind of tell that there's some sort of interesting oscillations kind of going on here. So, like I said, very micro scale. It's really for when you really understand the small scale interactions between agents, but you don't quite know what happens when you put a whole lot of them together. Like in this case, we kind of know how to make grass grow. We kind of know how to make sheep eat grass. We kind of know how to make a wolf eat a sheep it found, but we don't really know what happens when you put a lot of wolves together, or a lot of sheep together, or a lot of grass together. We don't really know what happens when you make the grass regrow fast or regrow slow. I mean, how does the grass affect the wolves? I mean, those are the sorts of questions that are interesting to ask here that you might be able to ask in mathematical frameworks, but when the space really matters, when it really matters that maybe all your wolves can get stuck up here and all your sheep can get stuck down here, that's when the agent-based model really becomes useful. So they were originally used as a tool for understanding natural systems. So the kind of biologists were the first to get at this, and they called them individual-based modeling, or IBMs. And they would model things like fish schools and bird flocks and complex kind of ecological system interactions. And then independently from that, the social scientists got involved, and they're the ones that introduced the term agent-based modeling to describe these computational social simulations of human behavior. So how do you test if you find a bunch of pottery in a particular area and you are not quite sure how it could have gotten there? Can you build a simulation of people that could have lived in that area and see if artifacts end up getting deposited by your simulation in a similar pattern as the actual pottery that you've dug up in the real world? That's kind of an example. But you could also do modern societies, so you know how certain individuals move throughout a city, but you're not quite sure what happens when you put a bunch of those people in a city and maybe scale the number of people up. And so that's kind of the modern societies or organizations, stock markets. And then the social scientists also got interested in these so-called participatory simulations. So what we do with that is you can actually have the agents being driven by real people as opposed to algorithmic rules, and you can connect all these agent-based modeling tools together over a network, and now this provides you kind of an artificial world in which you can manipulate interactions between people and study what distributions you get out when people are constrained to behave in such a way that you kind of force them to behave inside these agent-based models. So those are kind of different ways to apply those. Engineers typically they do something very similar, but they refer to it very often as multi-agent systems. And whereas agent-based modeling and individual-based modeling is typically used for the analysis of natural systems. Multi-agent systems is often thought about for the technological design. So I might use a multi-agent system framework to say, how do I build 1,000 robots that move around an arena and behave in a particular way, and I want to make sure all of them end up achieving some goal. Well, I might use a multi-agent system framework to simulate those robots to see if that happens. But the underlying frameworks are nearly identical for both the multi-agent systems and the agent-based models or the individual-based models. And although the accompanying auxiliary tools that typically go along with them might look a little bit different, but the major difference between multi-agent systems and agent-based models or individual-based models is culture. Whether you're a life scientist or a social scientist or an engineer, so the engineers might look down on agent-based modeling, but they might be totally fine to do multi-agent system simulation, which to me I think is a little silly, because if you look at the multi-agent system simulation tools, they're really no more sophisticated than the individual-based modeling or agent-based modeling tools. But so in general, at your level, I just say know these terms: IBM, ABM, and NAS. And for all intents and purposes, up to, say, explaining 95% of the variance between them, they're identical. All right, so popular simulation frameworks, NetLogo, which is the subject of Lab 4. NetLogo is related to a wide variety of other logo packages like StarLogo, OpenStarLogo, StarLogo TNG. These are they're all in common that they're sort of very sophisticated derivatives of the old Logo programming language, which is the language that was kind of meant to introduce children to programming. And they realized that, well, if this was amenable to sort of teaching children how to move these so-called turtles around a screen, then maybe we could actually introduce it to people who are normally intimidated by programming, like behavioral scientists. And so they took the kind of simplicity of Logo and they made it sophisticated enough to do a wide variety of things, but to do it in a way that looks very different than what you'd see in like C or Java, and that ends up taking the edge off of the programming. I mean, I know I have colleagues who are deathly afraid of mathematics and don't view themselves as programmers at all, who have backgrounds that maybe there's a little bit of statistics, but the last time they took a real math class was back in high school, and they feel extremely comfortable inside NetLogo for whatever reason. So it's still programming, but yeah. Now, if you really want to go to something like Java, but you want something that still does a lot and looks a lot like NetLogo, then there's this tool Repast, which is a Java-based agent-based modeling program, and it has sort of a skin over top of it called Relogo, which allows you to even load NetLogo models, and so it's really, but then sort of effectively program them in Java. And then there are there's toolkits for Python to do agent-based modeling and all sorts of other sophisticated agent-based modeling tools. Like Altreva is a very sort of expensive commercial program for doing agent-based modeling. AnyLogic, which you can see in IEE477 which does system dynamics modeling, and DES also does agent-based modeling, and sort of it's an industry leader in doing this, and again, it ends up kind of flirting with the Java side of things. So when you need to do something more sophisticated, you end up writing kind of Java code behind the scenes inside AnyLogic. But a lot of what you can do, you can kind of do graphically, similar to you do in other frameworks. Okay, so agent-based modeling, we'll see in labs 3 and 4. The basic lingo here is that agents are the entities. They interact with each other in the environment. Time can flow pretty much however you want it to flow. It can flow in irregular jumps, so you can build sort of a discrete event system simulation inside an agent-based model. You can do regular jumps, which is much more common. So you can have you just move the world ahead by a regular time interval and then ask, how did the world change? And it may not have changed, and which is kind of like a wasted time interval, but But you just may not have the ability to predict when the next time it'll change. So that's the best you can do. You can have agent-based models flow, so you actually can have variables in agent-based models that are continuous, and then you can have mixtures of all of these different things. We view the agents as concurrent processes that have the ability to alter the environment around them. So um, you you can think of two agents. One of them might end up modifying the environment, and the other one might then pick up on that modification and change its behavior. And so when you build an agent-based model, you have to be very careful in sort of determining the order in which things happen, because the computer actually can't have all the agents operating at once. It does have to pick an order. And so the scheduling of how these agents are implemented in the simulation can sometimes change the outputs of the simulation. So a good simulation will be invariant to those things, or at least you have to be sort of sensitive that those things might matter. These are microscale simulations, so they simulate the kind of fundamental processes at the very bottom of a sort of a process. They involve space and movement. They can be very fine-grained. They have very few sort of assumptions on everyone must move from A to B. They just say everyone must move, and then they just let them move and see where they end up moving. So they're very general purpose. There's a lot you can do with them. The downside is that they can be very slow compared to other simulation frameworks that can buzz right along because they make so many assumptions. So, as I've kind of hinted at here, a lot of these tools overlap. So as I mentioned, ABMs can actually have some DES inside them. You can use Monte Carlo methods on sort of all of these simulation frameworks. You can do things like run an ABM to generate probability distributions that help you parameterize a DES. And so you kind of can run the ABM first, but the ABM might be too slow to end up doing more sophisticated hierarchical modeling. So you end up then coarse graining the ABM into a couple parameters that you put in a DES that runs much faster. So, and so on and so forth. And so that, and then I mentioned also an ABM can be used to validate the use of an SDM. So you might say, like, your SIR model, you might not really be sure that it's valid. So you generate a kind of disease spread model with actual agents that move around a world inside an ABM. And if they end up looking like they're giving you the same results that the mathematical model without movement is giving, then you can trust the mathematical model. So all these things can go back and forth. You just kind of got to pick the modeling technique that fits best to your question and your constraints, computational constraints, and whatever else. All right, so last kind of example I want to give here of the value of these is another article you can read in, it's actually that same ORMS Today journal magazine that I mentioned earlier, but a different article, The Pedagogy of Zombies. And so, again, I'll put this up on Canvas, but there was a company, LMI. They're a not-for-profit strategic consulting firm that works for NASA, and they're interested in understanding commercial airlines and how they would respond to different scenarios, and how customers might be involved in all these things that would actually be great to for an agent-based model to model. But they had this issue that whenever they took interns, industrial engineering interns, and they employed them, then none of the interns were familiar with agent-based modeling, and they'd have to teach them the agent-based modeling in order to get them even up and running for them to do anything useful. And so they said, well, maybe we can kind of do something fun with this. Why don't we create a funny scenario, a zombie apocalypse scenario, where it is a NetLogo agent-based model where there's zombies that are unleashed on this world, this NetLogo world, and the students will have to build rules for the humans running around in the model to hide and avoid the zombies. And then these will effectively be stochastic simulations, and so they then can run these sims over and over and over again and then see how many of these sims which behaviors end up doing the best facing these zombies. And so you not only have to build it, but then make inferences after you run these experiments. And I think they said it was very successful in getting their interns engaged and learning about NetLogo and thinking about modeling processes that might actually be valid in these more industrial settings. So this competition then has been now repeated by Rochester Institute of Technology's Industrial and Systems Engineering Department, and it's actually sponsored by Informs and now IISE. So yeah, this sort of shows that there is a demand for students to become more familiar with agent-based modeling, which is why I like to at least introduce it in this class, because it's definitely very closely related to stochastic simulation. We haven't quite gotten to the point where we necessarily have an entire course on agent-based modeling for you, but we might get that way. In fact, in other schools, so here's an example, by the way, of that agent-based model with the zombies. So this is basically a building with lots and lots of rooms that zombies move through and people move through. There are zombie parameters, and you can adjust the behavioral rules for the people and run these things and see how well people survive. So in general, though, I mean, so this is kind of this is a fun example of something that agent-based models do, but I've mentioned these examples in previous classes, but, companies like Southwest use agent-based models to improve their operations of, how people sit, how cargo is loaded, things like that. If you want to learn more about agent-based modeling, there are some resources at ASU outside of engineering. So we have this kind of complex adaptive systems sequence that runs, and so this is actually a graduate level sequence, and you can see that some of the courses that are available to the graduate students taking this sequence actually involve agent-based modeling, and so they're under the AML prefix, the PUP, the CES, and the PAF. So there's a bunch of people from the social sciences who are doing agent-based modeling, these sort of courses. I just wanted to highlight sort of what one of these courses looks like, AML 520. So they use this textbook by Railsback and Grimm. So it's a really nice textbook, and it's got a nice website that you can go to find more details about the book. If you're interested in ABM and can't take the course, definitely recommend taking a look at the book. If you were to take the course, you would end up seeing that you have lectures on Tuesdays and NetLogo labs on Thursdays. And this is kind of an example of sort of the things that they go through. An intro to ABM, intro to NetLogo. They use something called an ODD protocol. This is how they publicize their NetLogo models after they're built in a way that kind of focuses on reproducibility. And then they go through different ways to do different sort of modeling approaches, and how you build the models and then how you analyze the models. And so it's a nice course that kind of, you can see it sort of follows a similar flow as this course, but focused on ABM. For undergrads, there are occasionally undergraduate courses in the AML and ASB prefixes and I think now you might be able to find some in the sustainability prefixes as well. And these are focus on agent-based modeling. They actually meet some general education requirements for students, and they typically also are focused on using NetLogo. It's a popular tool for agent-based modeling here at ASU. So you find them, they've got lectures, computer labs, homework assignments, and I think, yeah, all of the ebook that goes along with this course is totally free. It was written by the instructor. So if this is something of interest to you, then take a look, look through the master schedule for social simulation. And social simulation, even though it doesn't say agent-based or doesn't say NetLogo, that's what it is. It's an agent-based modeling course for modeling people, just like the zombie case, using NetLogo. Then there are sort of one-off things. So I've actually taught workshops here at ASU where it's like a day or two where students and faculty who want to learn about agent-based modeling come in, and sometimes we provide free lunch and things. And so so those are things to look out for, announcements for those things. Otherwise, the student groups, I've seen them, student groups bring in people to talk about R, Python, etc. So I think this is also a great place for students to learn about NetLogo, to get together and, just in one night you can kind of learn quite a bit about at least how to get off the ground, and then you can cover the rest kind of on your own. And then on that subject on your own, I definitely recommend the Railsback and Grimm text, but there's actually now a new text by Uri Walensky and Bill Rand. And Uri Walensky is actually the author of NetLogo, and so this is a textbook kind of like right from the source. And so both of those are excellent textbooks on getting started in agent-based modeling, especially if you're interested in doing it with NetLogo. All right, so we're still a couple more questions that I want you to answer on Canvas, but that's about the end of what we're going to do for this lecture. If you're interested in finding out more details about NetLogo, then there is a pre-lab 4 slides that you can switch to here and watch, and then I'll give you, that will go into some details about kind of how NetLogo is set up and kind of helps you sort of prepare for doing activities like the activities in Lab 4, but this is sort of the end of the kind of basic overview of what I want you to know about these simulation frameworks and kind of the existence of NetLogo. So head back to Canvas, answer those questions, and that's all for this lecture.